problem is complex, partly because usually what happens is a wizard takes a molecule like this and says, hey, that's great, there's two atom types for the carbons. It's like aromatic and aliphatic, easy enough, and there's some that then dictates some set of parameters that get applied. And this approach, first I assign atom types, and then I use those atom types to look up parameters, is what we're starting to call indirect chemical perception. So some tool or human assigns the atom types. From the atom types, parameters are assigned, so the atom types have to encode all of the requisite chemistry, which is a catch-22 because you can't encode it until you've decided what's relevant, and you don't know what's relevant until you fit it. Yet this is particularly important. Now our human expert applies the same thinking to this molecule, and suddenly we have a Ca-Ca bond that's a single bond. And that's, well, a Ca-Ca bond is supposed to be an aromatic, so that's a problem. You can fix that. No problem. I'll just invent a new atom type, CP, so that a CP-CP bond is a single bond, but a Ca-Cp bond is an aromatic. And that fixes the problem, except then what about this molecule? Now we have a CP-CP bond that's an aromatic bond. When I said CP-CP is single, not to worry, I can invent another new atom type, CQ, which is the same as CP, which is the same as Ca, except that CP, CQ are aromatic, and CP, CP, and CQ, CQ are single. So now I've just had to invent two new atom types just to get this bridgehead effect in there. And this is how GAF and GAF2 deal with this problem. And that's, superficially that's fine, though it does result in a lot of extra parameters that you don't really need. So for this type of molecule, now I have a really large number of torsions that even GAF2 only knows a small fraction of. And this is difficult, not because the chemistry is so complex, it's just that because of indirect chemical perception, we have this process of first assign atom types, then use the atom types to look up parameters. So the atom types have to be very complex to encode all the chemistry that's needed. Why don't we just do this? These are aromatic, that's single, it's easy. Direct chemical perception would be take the molecule and look up what the parameters would be from the molecule rather than the atom types. And why don't we do that? Well, it appears that the answer is for no good reason, other than that it would have been too hard to change the legacy code that was used when these general force fields started being developed.
That was exactly the reason Peter gave me in 1998.
And that's what I talked to Junmei Wang about GAF, and he said basically he wanted to do direct chemical perception, but they told him no, it was going to be too hard. And CGenFF says something like, it doesn't say that, it just says that the first step in building a force field always involves assigning atom types.
Since the 70s.
So we are working on a modern starting point for force field parameterization, Smirnov. Sorry about resolution here. Projector, I guess. Basically, this is a molecule, and some parts of it are color-coded. There's some nitrogens here, some oxygens. In any case, this is a substructure search. They can match a bond. It uses a Smirks pattern, which is related to a Smarts pattern. And this is a substructure search language I'll tell you a little bit about and show you some more of later. I have some atoms color-coded. This is a carbon with 4 connections. I'm going to call it number 1. This is element 7 with 3 connections, so nitrogen with 3 connections, and I'll call it number 2. This is a single bond. That's a single bond. This is a double bond. Here's another carbon. This one is not labeled. I don't have a number next to it. And this is an oxygen with 1 connection that has a charge of 0. And so I'm color-coding these, and they can match different parts of these molecules. It matches 2 parts of this molecule and 1 part of that molecule. In this case, this is a substructure search that we're using to match a bond, because there are 2 atoms that are numbered here, 1 and 2. And so I'm going to be referring to the bond between these 2 atoms. So this is a standard substructure search language, and we can use it to assign force field parameters. I'm going to be talking about a little more about this later after John has talked some about parameterization, but really this solves a lot of issues with extensibility and flexibility. Here's a table you'll be able to see better in the PDF because of resolution issues that has a bunch of components of the substructure search language. Basically, it's a pretty complete substructure search language, kind of based on smiles. So that gives us a language to express chemical perception, smirks, and then...
So there's some extra constraints too, like what we're dealing with has to be a connected subset, the tagged atoms have to be all connected to each other too, so in principle it's a subset of smirks.
Yes. And so it gives us a language to express chemical perception. Caitlin will talk to us a little bit later about sampling over chemical perception using this language automatically. But basically, we can start with some base components like elements and some decorators that describe the chemistry around an atom, like how many hydrogens it has connected, what valence it is, whether it's aromatic or aliphatic, what charge it has. And we can make Monte Carlo moves in this substructure search space and come up with, again, sorry about the resolution, relatively complex patterns that encode a particular type of atom connected by some type of bond to another type of atom. And those can capture different types of chemistry. And actually, the way this works is we can start with some initial force field guess. Actually, at this point, we're just looking at atom typing with this, but eventually we'd be using it for parameterization. So we can pick a parameter from a current list and then propose some Monte Carlo moves, such as deleting the parameter or creating a new child parameter, which might have a different type of atom or a different type of bond. Maybe the atom has a new substituent or gets deleted, or we change a decorator on the atom or the bond. We add an or an and some new type of decorator. And then we can see whether that improves our outcome. Now, our outcome in general might be our ability to reproduce specific properties we might calculate, or in this point, we're just asking, make sure we can sample the right thing. We're checking to see whether we can learn how to reproduce existing atom typing or existing parameter types. So we've tested this approach some to see if it can learn how to reproduce existing atom typing. For a simple set of molecules, it ends up coming up with this tree of atom types. Smirks patterns corresponding to this tree of atom types, and the patterns are shown over here that you can't see. We've taken this and applied it to a set we call mini drug bank that contains all of the atom types from a reference force field that occur in drug bank. And we're looking at running Monte Carlo simulations at different pseudo temperatures and asking how well we can learn the atom typing corresponding to this force field. This represents a higher success rate. And what we're basically seeing is that, so the color coding is how often we can, at least some of the time, find all of that atom type. So black means we're very successful at finding all of that atom type. There's a couple here that we never find, but aside from that, and I'll come back to those, we find all of the different hydrogen types in mini drug bank.
Is this meaning basically that it's a very rugged landscape in atom type space? Is that because you have higher success rates at...
Yeah, let me come back to that thought. So then we also have oxygen here. Again, we can find almost all of the types in oxygen, at least at some temperatures. Lower temperatures is harder. In terms of how rugged it is, I think that's right. Also, there's some that we don't actually expect to find, like HX, which basically is multiple. It's a type that Chris invented to be hydrogens that look like hydroxyl hydrogens, but not like those in water. And it's a combination of several different Smirks patterns. It's basically hydrogens that he needed to add Leonard-Jones parameters to.
Just for stability.
For stability. So we don't think we should be able to recover that.
Look, I'm just expecting a lot of wizard bashing this.
He added it for good reasons, but it's like the hydrogen that's different hydrogen.
But it's in principle in ours that could be the catch-all, right? Like the base type, but we don't allow base types here. Is that?
We can come back to that when Caitlin's talking about it.
I guess the other, does that mean that you potentially want to have an or on a couple of smirks or a few smirks.
Yeah, if we didn't need to learn it, we would or a whole bunch of them. But partly we're sort of saying, well, that was a thing that a wizard came up with, and we don't necessarily need to.
I think something like Ajax, that I had to come up with it as an expediency to deal with shape failures in Amber. It doesn't really reflect a sound chemical reality, or let me say it's a highly obfuscated chemical reality. So to have a method like Caitlin's, which is biased at saying, if we can't do this with chemistry, I'm not sure I can find it. It's almost a positive test to say something that is not a chemically based atom type, really. You're not really expecting to find it by a chemistry based approach.
Mm-hmm.
Yeah, I don't think there's any way that it could be the generic, John. We can talk about more details if you want.
Got it.
But I guess the question is there a scenario where one would want to be able to OR several smirks?
Yeah, and we certainly can do that, and some of them do, especially in Smirky, what Caitlin will talk about. But this one is especially honored. So ruggedness. Another factor that comes in, John, is that there are just very few of some of these, which makes it hard to find H2, H3, and H4, for example. When you find them, they tend not to stay around very long because there's like 3 or 4.
So they're entropically disfavored because they don't figure very well in the likelihood function that's constructed.
Yep.
So that it's doing as intended.
Exactly.
It's trying to minimize complexity.
Mm-hmm.
But this I think is going to be really, you've got to ask yourself about the abundance of certain kinds of really important chemistry. In other words, if the chemistry is really important but it's not very abundant, will we be punished by this entropy?
Right, but that's a matter of like how do you weight these in your likelihood function? Right now, everything is just like you're scoring how many matches you get in total, right? Where everything is the same cost, right?
So what that should come out with is that if it's giving predictions that are not good, that should be
for a real likelihood function. If you're
Yeah,
like your
exactly.
physical property would be 10 sigma off or
Right.
something like that because
even if
you get
it's
the
a small
density
amount,
so
it's
wrong,
10 sigma.
then it's going to contribute more because you're so wrong.
Yep.
So right now everything is penalized exactly the same. So
So I think this will come up more in your talk next, right?
So what we need to do is make sure the penalties there are appropriate.
yeah.
We should have somebody making notes of things we should talk about later. So I don't know if that one should be done on the board or in the bottom of the Google Doc. Any preferences?
Does somebody want to start a post in the Slack that we could just add to or?
Yeah, I can do that.
So, oops, my conclusions are out of order. So we want to automate force field development. Partly, we have smirks patterns which provide a language that we can use for chemical perception in these, so we don't have to decide the atom types in advance. We're going to need a lot of data, so we're going to rely extensively on NIST's ThermoML, and I apologize, the order is gone wrong. Working on automating it, yay. And sorry, Chris, we're trying to get rid of wizards.
Yeah.
The wizard is
I'm
going to help
actually
us.
a contributing factor to that too. I'm trying to get rid of myself. So.
So anyway, there's probably too many people to acknowledge, but really appreciate everybody who's been involved. And so for those who don't know, basically this effort started in this room, March 2016. We had this sort of PI lock ourselves in a room for 2 days things with Mike Gilson, Chris Bailey, John Cadera, Michael Schurtz, and it was really great.
The gestation goes back much further with many conversations over picnic tables at GRCs and at ACS meetings.
Science at its best.
All right, so John is going to tell us about how Bayesian parameterization would work. Does anybody have other questions first?
One thing we can do is we can refine the way we describe these approaches. I think your presentation was actually extremely clear about what the goals were. What do people think about the meat grinder analogies? That was just sort of almost a joke, but I think it lightens the
As a vegetarian,
mood a little bit.
You want carrots?
I tried to do an orange juice one because I didn't like the meat grinder.
Fair enough.
I couldn't make the
But
orange
the meat
juice.
grinder is held up as something that's bad. So it's
A lot of the junior research
maybe our end goal. Maybe we should the transition should be we're gonna get rid of meat grinders and have a veggie grinder.
There you go.
Yeah.
What about carbohydrates?
I think that the junior researchers might not realize how many grad student hours have been.
Yeah, how many
wasted is not quite the
PhDs?
right word, it's close. Trying to come up with models that fit in a sort of semi-blind way, just trying to poking at saying maybe these parameters work, maybe these parameters will work. And I don't think you realize what we're trying to save you from. So I think meat grinder analogy, just like sending troops to the battlefront where they just get worn.
Oh, so the meat isn't the data, it's the student.
It's the
We didn't want to miss the whole part.
Yes, absolutely. We're trying to save people from that.
I think that
It's like World War I, where you just throw people on the front line, and eventually, you just through attrition, you manage to make progress.
So it's the student going through the machine.
Yes, yeah.
this highlights a good principle, though. Like anytime we can engineer a more simple, general way of doing something, we should try to prefer that method if it's going to have life beyond the simple. Like if you find you need to have a workaround or a one-off, that's probably something is wrong. There's something fundamental that we should be thinking about instead.
I think part of it is one way that's possible to change now is that computation is so much faster. Is that rather than guessing things, you can just use computers to
And
brute
data.
force evaluate the possibilities, and you're focusing your mental effort on the hypotheses rather than the trying to figure out what